Okay, so this is going to be our second lecture for chapter 4. And so today what we're going to cover is our redox activity series, our redox equations, our activity series, and then the solution stoichiometry. And so a little bit of a review. For each of these, we want to think about what we would have inside of that solution if we had this material dissolved into it. So this is K2SO4, we have NH4ClO4, and we have C6H12O6. And so we should be able to go through and we should be able to answer this. This is a little bit of a review from last time. So you want to think about whether you have dissociation or dissolution. You also want to think about whether you form ions or not. So looking at K2SO4, that's an ionic compound. And so if it's an ionic compound, it should split into its cation, the K+, and its anion, SO4, 2-. Now we shouldn't split up that sulfate anymore because it's a polyatomic ion, so it stays together all as one unit with that charge. So we don't want to split into sulfur and oxygens because in reality, when it dissolves, it's going to stay together as that polyatomic ion. Next one, NH4ClO4. That's actually two polyatomic ions together. We have ammonium, NH4+. We have chlorite, ClO4-. And the last one, we're looking at glucose here, C6H12O6. And that is a trick question. That does not dissolve or disassociate inside of the water because it's a covalent compound. There's no metals in there. There's no polyatomic ions. That means that we should have no ions present when we form that. Next scenario, which of the following will occur when solutions of copper sulfate and barium chloride are mixed? Do we form a precipitate? Do we not form a precipitate? And if we do form a precipitate, what is going to be our spectator ions? We should create our box. We have our copper 2+, SO4, 2-. We have our barium, Ba 2+. We have a chlorine 1. So we should have copper chloride, CuCl2, barium sulfate. So we don't have to worry about. Looking at the solubility rules, one of those does form a precipitate. BaSO4 is not soluble, so that's going to be our precipitate as our solid. That brings it down to these last two. And so then what do we have left over? Well, we have copper 2+ and chloride. Those are our spectators. Okay. Next part. How many milliliters of 0.610 mils molarity NaOH solution are needed to neutralize 20.0 milliliters of a 0.245 molarity H2SO4? Pause this. Don't go any further. You want to try this one out. This is a great question because you've done something similar with our acid-base neutralization from before. All right. First step, when we get a problem like this, you have to figure out the chemistry first. We need to know what is reacting. So there's a key word in here. It says neutralize. Neutralize, we want to be thinking about acids and bases. So we have NaOH. We have H2SO4. NaOH is our base. H2SO4 is our acid. Neutralize means we make water, and we also make a salt. So what do we have to make our salt? That's our Na and our SO4. And if we make that as a compound, that should be two of them. That's aqueous because it's definitely soluble. That's a liquid. So now we need to balance that out. So we should have 2 NaOH to every 1 H2SO4. And that's why we have to make that chemical equation, because they're not equal to each other. We need twice as many of them. And now from there, we can do our next step. We can say, so we're going to start with what we know. We know our H2SO4. So we have 20.0 milliliters of H2SO4 solution. 1 mole of that, 1 liter of that is 0.245 moles of H2SO4. Now, so far our units won't cancel, so we got to get our milliliters into liters. So 1 liter is 1,000 milliliters. And now we know that inside that sample, we have 0.245 times 20.0 divided by 1,000. We have 0.00 moles of our sulfuric acid. We can then take that moles of sulfuric acid and we can turn that into our moles of our NaOH and then get that into a volume. So 0.0049 moles H2SO4. We know that if we had 1 mole of it, we can make 2 moles of NaOH. And we know that if we had 0.610 moles NaOH, that would be 1 liter of solution. And we know 1 liter of solution is 1,000 milliliters. So 0.0049 times 2 divided by 0.610 times 1,000. And we find out we need 16.07, 655, but that would be 7 milliliters of our NaOH, which is really 16.1 when we think about our sig figs. So we should have a total of 16.1 milliliters NaOH. Okay. Now, we should also be able to answer this question. How many moles of NaCl are there in 200.0 milliliters of a 1 molarity NaCl solution? We should also be able to turn that into grams. A little bit more straightforward. So take a moment, figure that part out. There we go. We take that milliliters, we turn it into moles using our conversion into liters and then our molarity. Once we have those moles, we can use our molar mass in order to get it to our grams. Now remember, we have 4 sig figs here. We only have 3 here, and so that's why our answers are only in 3 sig figs. Let's do a dilution problem. What volume of 0.50 molarity NaCl stock solution is needed to form 500.0 milliliters of 0.15 molarity NaCl solution? So this is a dilution problem. So you can do this as M1V1 equals M2V2 because it's the same solution. That is possible. I'll show you how to do it a different way. One is we can take what we know, 500.0 milliliters. We can turn that into our moles. So that's 1,000 milliliters is 1 liter. 0.15 moles is 1 liter. And so this tells us how many moles we need. 500 divided by 1,000 times 0.15. So we need 0.075 moles. Now, I can take that 0.075 moles of NaCl, and we're going to get that from our stock solution. So that's 0.50 moles NaCl inside of 1 liter. And just because everything else was in milliliters, why not? We can keep that in milliliters as well. And we find out that that should be 150 milliliters of 0.50 molarity NaCl solution. Same thing, it will also get us that M1V1 equals M2V2 also would have worked. I like this method better because it's the same method that we use for our acid-base titrations as well, just not quite as many mole-to-mole conversions. Right? But if you like the other one, M1V1 equals M2V2, you have it as well. So just be aware about them. I won't ever give you the M1V1 equals M2V2 equation on your equation sheet because I think that you don't need to memorize that. Right? You can use your dimensional analysis and it's just as good. Now, the reason why we want to keep practicing with this is you can imagine that molarity is the key. It's the key for converting our volumes of our solutions into moles. Because once we have them in moles, then we can do our moles to moles. And so the key to that transition is molarity. In the same way that the key to going from moles of one thing to moles of another is our chemical equations. That's how we can make those transitions. So we can start adding this into our stoichiometry problems, because now instead of just starting with our grams like we've been doing in chapter 3, we can also now start from our volumes as long as we have things like our concentration factor. So as long as we have things like molarity, or maybe even the mass per percent, things along those lines. They're just another tool in our toolbox. Okay. The next thing that we're going to talk about is this is going to be about oxidation numbers. Now, oxidation numbers are an interesting thing inside of chemistry. They're also called oxidation states. And what they're talking about is there a way for us to look at a compound and determine how their electrons are being kind of like divided up inside of them. And so this works very well for our ionic compounds. It's not so great about covalent compounds where we start to share things. And so they're not always directly tied to the physical situation of what's going on, but they're a starting point for that. And so there's a couple of different ways to find out your oxidation states or your oxidation numbers. One of them is there's a list of rules that you can just memorize. Those lists of rules gives you an idea about how to break things apart, what to kind of look at, what kind of general trends do they follow. That is helpful. Another one is you probably already know a lot of them because you already know what common ions they form. And so in the same way that you can figure out for an ionic compound what their pieces inside, we can also use that to determine our oxidation states. So the big rule about them is, let me move this over here. Number one, any compound that's by its, or I'm sorry, any element in its elemental form, its oxidation state is going to be equal to 0. What that means is whether that's H2 or Ne or O2 or Al, when it's by itself, it's going to be equal to 0. What that's trying to tell us is that their number of electrons, so their charges, are going to be equal to what they would naturally occur as. So as long as it's in this elemental form as it naturally occurs, then it's going to be equal to 0. That also makes it easy when we talk about ions. Ions are equal to the oxidation state when it's just one atom. So if we were to look at H+, it's got a +1 charge, and so its oxidation state is +1. F-, it has a -1 charge, so its oxidation state is -1. The idea is that oxidation states help us keep track of our electrons and where they're moving around to. So if you have a negative oxidation state, it means you've gained electrons from your base value. If you're positive, it means you've lost electrons from your base value, just the same way that ions and their charges tell us. So the charge of the ions are equal to the oxidation states. Number 3 is that all of your compounds, when we add up their oxidation state, it's going to be equal to their charge. So something like Fe2O3, because it's neutral, all of their oxidation states should add up to 0. Whereas something like carbonate, CO3 2 minus, all of its oxidation state should add up to -2 because it has 2 extra electrons in there that have to be accounted for somewhere. Now, from there, we can start to piece together our different compounds. So if we look at Fe2O3, we can assign their oxidation states based on their ions that they should have formed. So we know for Fe2O3, our oxygen should be our 2 minus. And that means that if we have 3 oxygens at 2 minus, then our iron has to be 3 plus in order to balance that out. So in the same way that we used to find charges, that can also be useful when we first start to do our oxidation states. Now, I think that this can get a little bit confusing. So instead of just talking about it, why don't we do it? So let's look at this compound here. This is iron plus oxygen gas going to iron 3 oxide. And so we want to start to assign our oxidation states. So this iron should be a 0, and this oxygen should be a 0 because they're both in the elemental form. And so then in our Fe2O3, this should become a +3, and the O2 should become a -2 based on the ions that they normally form. Now from here, we're going to introduce 2 terms. We're going to introduce oxidation. We're going to introduce reduction. Now, oxidation means that you lost electrons. Reduction means that you are gaining electrons. I guess instead of lost, we should say that they're losing electrons. So if we're thinking about this, our iron is going from a 0 to a +3. So did it gain electrons or lose electrons? Now it's becoming more positive, so it's lost electrons. It's giving them away. Oxygen, on the other hand, it's gained electrons, so it's reducing. So each iron is oxidizing and losing 3 electrons each. Each oxygen is reducing and gaining 2 electrons each. And so if you wanted to think about this, one way to remember that is Leo the lion goes grr. And that means that when you lose electrons, you oxidize. When you gain electrons, you reduce. Your oxidation number is going down, so you're reducing. Now to even confuse that even more, when they talk about oxidizing agents, right? Agents mean that you are creating that. So instead of you being the one oxidizing, if you are an oxidizing agent, you are causing something else to oxidize. So you are the cause of it. Reducing agent means that you don't reduce, but you cause something else to reduce. So if you really think about it, the oxidizing agent is the thing that reduced. The reducing agent is the thing that oxidized. But they're the ones causing that change. So if we were looking at this example, the oxidizing agent in this case is our O2 gas. It's the thing that has caused the other one to oxidize. Our reducing agent is our iron. It caused the oxygen to oxidize. Sorry, it caused the oxygen to reduce. So you always have them doing the opposite of what kind of agent they are. If you're an agent of change, it's not that you are changing, you are causing other things to change. So that's kind of the idea. Oxidizing agents don't mean you oxidize, it means you cause something to oxidize. Let's look at this one. Let's assign our oxidation numbers and let's see who's gaining electrons, who's losing electrons. So Na and Br. Well, sodium we know is a +1 in its charge, and bromine is a -1. Magnesium from the periodic table, we know that's +2. Oxygen, -2. MgBr2, well, magnesium still would be a +2. Bromine would still be a -1. Sodium still a +1. Oxygen still a -2. And so now when we look at that, did any of them change? In this case, none of them changed. And so this is actually not an example of a redox reaction. So a redox reaction is going to have two parts. Redox reactions should have something that reduces and then if something reduces, there must also be something that oxidizes. And that's where the redox comes from, right? Red from reduces, ox from oxidation. Let's try another one. Each calcium is blank and blank electrons. Each H plus is blank and blank electrons. So we assign our charges, and we should have this as each calcium is oxidizing and losing electrons. Each H plus is reducing and gaining 1 electron. So for something like this, what I really recommend is practice, practice, practice. And so I'm going to add on to this lecture a worksheet, and we're going to end the lecture a little bit early so you can practice doing some of these redox equations. Now, when you balance redox, there's two things. You can balance them like normal for your chemical equations, except there's one other part that you have to do. You also have to balance the transfer of the electrons. So your electrons also need to be balanced. It's not enough to only balance your elements. You also have to balance your electrons. And so one way to do that is using something called a half reaction, where we look at only the part that oxidizes, only the part that reduces, and then we add them together. And this is because electrons that are lost by one substance, they're going to be gained by another one. They're not going to disappear. They have to show up on both sides. And so electrons are never created or destroyed through this process. They can only be transferred. So this is our net equation. We have our tin, and it's going to oxidize because it's going from a +2 charge to a +4 charge. Our iron, on the other hand, it's reducing. It's going from a +3 charge to a 2+ charge. So when we want to split that out into a half reaction, we can just say, well, tin 2+ goes into tin 4+ and then loses or produces 2 electrons. On the other hand, iron 3+ goes to iron 2+ and it does it with 1 electron. So if we want to balance these two, then we need to change them so it's 2 electrons in front of our iron reduction. So that way it can balance out with our 2 electrons from our oxidation. That's why when we have this equation, we ended up having to put in these 2's here in order to balance our electrons that are transferred. And so the oxidation half reaction will always have those electrons on the product side. The reduction reactions will always have them on the reactant side. And so when you balance them, you have to balance both of those sides together. Okay, next one. There's a couple of terms that get associated with these chemical equations when we talk about electrochemistry or when we talk about these redox reactions. And that's about energy. And so there's 2 different ones to talk about. One is electricity is the movement of electrons from one point to another. So when you turn on the light switch, there's a chemical reaction somewhere that's creating electrons that can travel from one side of that switch to the other. They lose their energy, giving us that power. And then they travel back to where they came from to complete the loop. So we're constantly moving those electrons around. Voltage is the push of those electrons. So that's how much energy that electron has as it moves through it. So you can kind of imagine in terms of water that your electrons have a starting amount of electricity, and then they have what happens afterwards, and that changes their voltage. So the bigger the voltage, the more energy they have. So things like lightning have very large voltages. They could do a lot of change. There's a lot of energy associated with that. But current is the amount of charge that passes in a certain amount of time. So it's kind of like how much water. So it's not how quickly the water comes out, but how much. So something like a river might have a really low voltage if it's moving slowly, but it could have a really high current if there's still a lot of water moving that way. Lightning, while it had a high voltage, has a very low current. There's not much of that electricity inside each lightning bolt. And so while it has a lot of energy in one ways, because it doesn't have a lot of electricity, its current is very low. So it's different in that regard. You can kind of imagine amperage as being like a hose size. So the one with less, this might be like a garden hose. So the water might come out at the same speed, but not be as much. Whereas if it's a larger amperage, maybe this is like a fire hose. Similar speed that the water comes out with, but a lot more volume of it. And so that's the difference between voltage and current. The other part about redox is what we call our activity series. So the activity series is one quick reference guide to see what metals are more likely to react or not. We saw this in lab when we were looking at the periodic table groupings, and I showed you an example of lithium reacting potassium, sodium, francium, cesium. Those different activities showed us the different kind of reaction speeds and kinetics that they had associated with it. This activity series is kind of putting them together, not just in one family, but across families. And what we're looking at is we're looking like how likely are they to oxidize. So the more likely that you are to go from lithium as a solid and lithium as your ion and to lose your electron, the more active we label you. The less likely you're to change, then the less active you are. So things at the bottom are generally things like our precious metals, things like gold and silver and platinum. Part of what makes them so precious is that they're very inert, in that they don't get involved in a lot of chemistry all the time. And they like to stay as they are. It's one of the things about why gold lasts for such a long time. And so the ones at the bottom, that doesn't mean they never react, but it just makes it harder to do. So the more above you are, the more likely you are to oxidize. The more below you are, then the less likely you are to oxidize. So when we look at a reaction and we're trying to decide whether it's going to occur or not, we have to make sure that it makes the most sense. And so we're going to look at what that looks like. So the first part is, let's look at our activity sheet, and let's just go ahead and label them as which one is going to be our most active to our least. So we're really starting at the top and we're working our way down. So lithium is here, platinum is down here, lead, Pb, is here, cobalt, Co, is right here in near the middle, bismuth down here, and mercury down here. So if we wanted to start to list this as our most active to our least, well, lithium is the most active, then cobalt, then we would have our lead. After our lead, we'd have bismuth. After our bismuth, we have mercury, and then our least reactive is platinum. Okay? And so that's the simplest part of our activity series. The next part is we want to think about our solutions and how different metals inside might react. So let's say that we have a container here, and that container has water inside. And inside that solution, we have these sodium ions. And so we're going to put into that a piece of tin, Sn. And we're trying to think if there's going to be a reaction that occurs. Is that tin going to stay as it is, or is it going to start to react with that sodium, and that sodium is going to become a metal, and the tin is going to become the oxide? And so how you do that is you look at where they are located on the periodic table. So tin, or not the periodic table, the activity series. So tin is here. Sodium is up here. So the more active we are, the more likely we are to oxidize. So if we have a choice, our tin should be the one in the oxidized form. So that's it after it's lost electrons. Whereas tin, being the less reactive one, should be more in its reduced form, which would be where it hasn't lost any electrons. And so in this case, we're trying to see, does it make sense? And so far it does. That tin should stay where it is because that sodium is more active than it, and so it's more likely to be the one to be the ions. But let's change that. Let's say that instead of sodium, what if this was silver, Ag+. So now we have silver ions in there. And so when we look at that, now it doesn't make as much sense because the silver is in its oxidized form and the tin, it's in its reduced form. And so that doesn't line up with their activities. Tin should be the one that's oxidized and silver should be in the one that's reduced. And so what's going to happen is instead of staying as they are in the way that tin metal would have sat inside of our sodium solution, that silver is going to start to take away electrons from our tin. That silver is going to start to slowly gather those electrons, one electron at a time, and turn into silver metal. Now, when it does that, that means it's going to force that tin to have to give up an electron and turn into its oxide. So over time, instead of just sitting there, that silver will start to plate out of the solution, it'll turn into its metal, and that tin will start to dissolve inside. And so this is why our different types of materials matter when we think about our redox equations. If our activities are lined up correctly, then that metal will stay as it is for a lot longer. If they're not lined up correctly, then they will slowly start to corrode as that metal starts to turn into its ions, or sorry, its oxides. And the other ones will start to come out and turn into the metal. And so a good example of this is the Statue of Liberty. Now, the Statue of Liberty wasn't always green. It actually is made out of copper, so it used to look just like a penny. But over time, that copper has turned into copper 2+, which is that green color. Now, as that's happening because of the weather, the way that it's been going on, what happens is that copper, its activity is down here, but on the inside of the Statue of Liberty, there's iron, which is higher in its form. And so what they started to notice was that those iron beams that were supporting the inside of the statue were starting to rust even though they had never gotten wet. Because what would happen was that the copper that was getting exposed to the elements on the outside that was getting weathered, it would turn into copper 2+. And then once it was copper 2+, once it was copper 2+, it would steal those electrons away from the iron that was on the inside, turning that iron into its oxide, so it's rust. And so it would slowly start to corrode it. And so over time, they had to start replacing these beams that were on the inside of the Statue of Liberty, so that way they wouldn't corrode all the way through and then fall down. But in some ways, that was kind of a win-win, because if the iron didn't sacrifice itself, if it didn't start to corrode, then the copper on the outside would start to deteriorate more and more and more, and eventually the Statue of Liberty wouldn't be there anymore. This concept, this corrosion of the metals, is a very important part when you get into engineering and about how you set up your system, because there will always be these chemical reactions that take place as long as there's weather. And so if we understand the correct pieces that we use, what we can do is we can create what we call a sacrificial metal, where we can use it to take on all of that weathering. So it does all of that work. And so we can make it so it protects whatever it's connected to. So sometimes you might see that next to a utility pole. That pole with all of its fancy metals conducting that electricity, we don't want that to break down. We don't want the transformers to weather. And so instead, we put down a simpler material, magnesium. We stake it in the ground and we connect it with a cable. And so now as the pole starts to weather and all of its fancy pieces of metal up on the top start to weather, they can pull those electrons away from that magnesium and regenerate or repair themselves. That magnesium instead sacrifices itself to that corrosion, which isn't so bad because then we can just come in, we can pick up that magnesium, we can replace it, and it can keep on going. You see this as well on big ships. Ships can have what we call as an oxidizing plate. So they can be just a piece of metal on their hull. And so instead of the rest of the hull rusting, where in order to repair it, we'd have to pull the whole thing out of water, sand it all down, put on new pieces of the hull. Instead, we can just look for this one plate. And as long as that plate we never allow it to go completely away, we can keep replacing it and keep regenerating that hull. Now, this happens often for things like building bridges. When you build a bridge, you have your different supports, but you also have the bolts that hold those supports into place. Now, one method would be that you just use really non-active metals for the whole thing. And that's going to give you a long lifespan without any corrosion or very little corrosion. But that can be expensive. It could also maybe not be the strongest one because not all of those non-reactive metals have very good strength properties. Now, if we make a mistake and we put the wrong metal as our bolt compared to our corrosion, what happens is that those bolts will start to corrode first before the supports. And so then they can corrode a lot quicker. That's a good thing in some cases and a bad thing in others. If we don't pay any attention to those bolts, so if we do it by accident, then the whole bridge will age much faster than we anticipate and it will collapse. But if we pay attention to those bolts, if instead we replace all of the bolts that are easy to reach with our sacrificial ones, so like our zinc or our magnesium, as long as we constantly replace those bolts, then the rest of our structure will stay fine. So in the same way that they replace those magnesium stakes, for bridges they can do a similar thing. If they can't completely weatherproof it, instead what they can do is they can make these, Instead what they can do is they can make these sacrificial ones that they can put on instead. So that's kind of the applications of the activity series. And so we want to make sure that we kind of understand what's going on with it. And so we want to practice. So does a reaction occur when an aqueous solution of NiCl2 is added to a test tube containing strips of zinc? So that means that we have zinc metal here. And inside of our solution, we have chlorine ions, Cl minus. We also have nickel 2 plus. So we're not worried about the chlorine. What we are worried about is that nickel. So we jump back here. We have our zinc up on top. We have our nickel down here. And so remember, whichever one is the up on top, that's the one that wants to be in the solution. It wants to be in its ion form. So does a reaction occur? Yep. That nickel will start to turn into a metal because it's going to gain those 2 electrons. Oh, put the 2 electrons over here. And that zinc will start to turn into its ion and dissolve as it gives away that 1 electron. And so if we wanted to balance that, we would need 2 zincs for every 1 nickel because zinc only loses 1 electron compared to the nickel. Now, what happens if we put both of them together? Now, if both of them, nickel 2 plus and zinc 2 plus, are reacting together, does anything happen? And in this case, our answer is going to be no, because there's actually no source of electrons that they can pick up. So because there's not zinc as a metal, that zinc has already given away its electrons. It's already there inside its oxidized state. So that nickel can't take any more electrons in order to turn back into nickel as a metal like it did back here. And so that's why we have no reaction taking place, is because there's no one there that can oxidize any further. Now, if you continue on into Chem 121, you guys would get a little bit more into this electrochemistry. So you guys would talk about battery systems and how you guys can use electricity to drive a reaction. But we just wanted to cover the basics, which is this redox part, that we can have electrons that flow from one side to the other. And so we can gain electrons and reduce, we can lose electrons and oxidize, and we can create different chemistries there. Now, before you guys finish up, there's a couple more practice problems that we want to do about our solutions. Some of them might be a redox reaction. Other ones might just be a straightforward titration. So in this case, we have potassium permanganate, and we need to oxidize 25 milliliters of iron to sulfate in an acidic medium. So the net ion equations show down here. For some reason, my reaction arrow turned into an R. That should be an arrow. So we have 5 irons plus our MnO4 plus 8 H pluses going to Mn2 plus 5 Fe3 plus 4 waters. And so if we look at this, this is going to be our oxidation. So 1 electron, there's 5 times of it. So we're transferring 5 electrons there. MnO4, well, we know oxygen's 2 minus. So that means that this Mn must be plus 7. And how we got that was that there's 4 of those oxygens. So that's 4 times 2 minus. And all of that is equal to minus 1. And we have 1 Mn that's kind of trying to fill that in. So Mn minus 8 is equal to minus 1. So Mn is equal to plus 7. So that means that it's going from a plus 7 on the reactant side to a plus 2 on the product side. So that's reducing. And it's reducing 5 electrons, so it definitely looks like we're all balanced. Good, success. So if that's balanced, then we know we want to start with what we know. So we know that we have 16.42 milliliters. We know that there's 1,000 milliliters inside of 1 liter. We want to get that into our moles. So we know that there's 1 liter inside of 0.1327 moles of KMnO4. We also know that there's 1 MnO4 inside of 1 KMnO4. And the next part that we can get it into is we know that we need 1 moles of MnO4 will get us 5 moles of Fe2 plus. And there's 1 Fe2 plus inside of 1 FeSO4. Whew. That is a lot of work for us to get to our moles. But if we check our units, milliliters cancel with milliliters, liters with liters, moles of KNO4 with our KMnO4, MnO4 with MnO4. And so then we have Fe2 plus with Fe2 plus. And so we're going to end up with moles of FeSO4. So 16.42 divided by 1,000 times 0.1327 times 5 And so this is 0.01089 moles of FeSO4. Now that's not enough. We can't just stop there because it doesn't ask us for our moles, it asks us for our concentration. So we want to take that, we want to divide it by our volume. So that was 25.00 milliliters. And remember, we need that in moles per liter. So we got to take that 25.00 milliliters, turn it into liters. And we get 0.4358 molarity FeSO4. There's also some other step-by-step instructions there. So if it was a little bit too much, you go through the slides and they'll take it a little bit slower with you as well. And so that's what we're looking for. All right. We're going to look at one more of these problems. In this case, we want to think about the amount of oxygen dissolved in water, and we can determine it by titration. So first, the MnSO4 and NaOH are added to a sample of water to convert all of the dissolved O2 to our MnO2. Then that H2SO4 and Ki are added, and the reaction is then set up as part 2. Finally, the iodine that is formed is then titrated with this Na2S2O3 by equation number 3. So it's a lot of steps that we have to do in order to find that next part. So according to the equation, how many moles of S2O3 2- are required for analyzing 1 mole of O2 dissolved in water? So if we put 1 mole of this, and we are trying to track that down into S2O3, so this one here. Well, if we have 1 mole of our O2, that's going to make 2 moles of that MnO2. And if we have 2 moles of that MnO2, then that's going to make 4 moles, or sorry, not 4. That's going to make 2 moles of our I2. If we have 2 moles of that I2, then that means that this needs to double and we need 4 moles of that S2O3. So we need 4 moles of it. And so now go ahead, try to tackle part B and part C. And then we're going to show you the answer on the next page. All right. There's one other question that I want you to go ahead and try. And so in the reaction vessel, we have some barium nitrate. And we're going to add in some phosphoric acid to it. And it's going to have a final volume of 2 liters. And so the reaction is shown below. So I want you to calculate how much of this you produced. And then what's the concentration of this one after the reaction? Your answer will be on the next slide. So I'll link to you the oxidation number so you guys can practice that. Otherwise, good luck.